topic tonight is about quantum computing. And before we get a little further into that, I'd like to introduce you to our guest. Our guest is George Musser. George is an award-winning science writer and journalist. He has worked as an editor for Scientific American, for Nautilus magazine, and many other places. His work is renowned not just in the writing world, but in the science world for its clarity, its depth, and its brilliance. He has some books under his belt, one of which is called let me see if I get this right, The Complete Idiot's Guide to String Theory. Yes, much read by certain professors at Columbia University. And his most recent book is called Spooky Action at a Distance, which is actually all about non-locality in physics, which is one of the most extraordinary, puzzling, and fascinating aspects of the natural world that I can think of. And in that book, George does, again, a brilliant job at not just explaining the science without dumbing it down, but painting in the colors of how this science comes to be, how this understanding of the world has implications for our whole form of existence. So without further ado, please give a round of applause for George, and he'll join me on stage, and we'll start this conversation. George. So we're going to get comfortable with our beers here.
Thank you for such a wonderful introduction. I need to have you introduce me everywhere.
Well, that costs something, so okay. You have to. So before we really engage in the conversation, I just wanted to, by way of a little bit of introduction, talk about my motivations for inviting you here tonight, because this is very, very self-centered. I wanted to have this conversation. It is all about me. I am the solipsist in the room. So we're going to talk about quantum computing, AI, and us, and so on, as the title of this event suggests. And I wanted to kind of explain why I thought this would be a good idea. And part of the reason is that over the last couple of years, I found myself in various situations where I've had conversations with people, and if we've ended up talking about science, we've talked about what YHouse is doing, investigating consciousness as a phenomena, investigating the nature of intelligence. Quite often, the conversation kind of drifts towards that person saying to me, well, once we have quantum computers, we're going to have quantum AI, we're going to have machines that are better than us at everything. It's just going to change everything. And it's like this mystical thing, quantum computing and consciousness and intelligence and so on. And my reaction to that is, huh? Partly because I don't fully understand or appreciate the details of what we mean when we say quantum computing. So one thing I'd like to do this evening is unpack that with your assistance. And actually, I feel you are absolutely the expert. And the other piece, eventually this evening, what I'd like to do is, as we unpack the details of quantum computing a little bit, get familiar with that, is take the arc eventually, I think, in the end of this conversation, towards those propositions that people make about, quantum computing is somehow this way to create artificial minds that are beyond anything else, and perhaps even there's a connection between the way our biological minds are working. We'll get to that. So I think the first place to begin is, and I'm going to shut up soon and let you do some talking.
You're doing fine. Keep going.
The first place to begin is with some basics, and I think we have to assume that I am, just like your Complete Idiot's Guide to String Theory, I am the complete idiot. It's not a stretch for me. Let's talk about the quantum physics, the quantum mechanics, the idea of computation in that realm. I mean, where do we begin? Do we begin with talking about quantum physics, or do we actually begin with the idea of computation itself? What do you think is the best way to begin this?
I mean, there's so many entry points to think about quantum physics, quantum mechanics, field theory, and all the things that we put quantum in front of. But in terms of quantum computing and maybe quantum artificial intelligence, I think it's instructive to begin with the basic unit of information, the bit. And one way you might actually think of a quantum computer, which operates on qubits, quantum bits, is it's an analog computer with a digital face. So there's kind of two levels going on here, and actually that's the case with quantum physics generally. There's the level of what we see and what we're able to observe, and then we think, there seems to be, and it's borne out by our experiments and our theories, a kind of substrate to that. So we don't see, for instance, a quantum wave function, but we do see what seem to be the consequences of that. And so it is with a quantum computer. There's kind of an analog computational level, but we see a digital computation or digital set of processes emerge from that, and I can be more specific. So if you start from the digital and kind of penetrate down to the analog level, your digital computer usually is based on the bit, so a 0 or a 1, like that might be represented by ground voltage, and then maybe 3 or 5 volts. Sometimes actually there are multiple qubits or things like this, but let's stick with bits for now. And the idea is that when you move from the bit to the qubit, you introduce a spectrum of possibilities, a continuous spectrum. It's an analog system. Continuous spectrum of possibilities, like basically intermediate between the 0 and the 1.
So that's a tricksy sort of concept. So, okay, so classical digital computer, a bit is either 1 or 0. And it is that, no matter what's going on. I mean, it is 1 or 0. Whether I'm measuring it or not, we think it's 1 or 0. Qubit, a little different, right? It's simultaneously 1 and 0 and everything in between. Or how does that? I'm just trying to.
You know, this is one of those things in science where a little creative license actually helps. So the unlicensed statement would be that actually is neither 0 nor 1. And then you begin to go down the rabbit hole thinking what that might mean, and it's actually a deep fact about the universe that particles, before they're observed, actually don't even have a position. The concept of category position or of momentum or their other properties is not even defined for them. David Albert, one of your colleagues at Columbia, compares it to asking the marital status of the number 5. It's just the category of marital status does not apply to a number. Likewise, the category of 0 or 1 actually does not even apply to a qubit in its native state. But let's be creative and license ourselves to think of it as it's simultaneously, or maybe in some intermediate state between 0 and 1. I think that's a good enough way of thinking about it.
Right. I mean, intermediate state feels a little more. I can grasp that a little bit better.
Yeah. So it's kind of halfway, roughly speaking, halfway between a 0 and a 1, or a third of the way.
More, just to have the technical term there, I mean, this is a state of superposition. Okay, so that's one of the terms that comes up when we're talking about.
It's a superposition
physics
of 0 and 1 in this case. It actually, what's interesting about quantum devices, and certainly quantum computers, is that the same superposition of 0 and 1 could actually be a different superposition of other, like up, down, or plus, minus, and there's different ways of describing this very same quantum state in terms of different superpositions. So the example we often give here is the Schrodinger's cat. Now, one thing that's is seldom pointed out about the cat is, so your Schrodinger's cat is both alive and dead.
So it's a qubit.
Actually, it is a qubit. It's literally a qubit. A very morbid qubit. But actually, even an ordinary cat, that's one is indubitably alive, it's also in a superposition of sort of, you might think of it as slightly alive and slightly dead, and another state that's slightly alive and slightly dead, and when you combine them, you get all alive. So everything in the world can be thought of as being in superposition. So your cat is a bundle of contradictions no matter what.
Now, is that all alive to do with interference, or is that something that comes later down the line when we're talking about this?
You can think of it as an interference phenomena. It's basically when you're combining states, you can have parts of them offset one another.
Okay, and I guess we'll get to how this is actually manifest or can be manifest in the real material world in a little bit. We'll get to, okay, this is the abstract picture of this qubit. So So a qubit, we haven't really said what you make it out of yet. We'll get to that. It has this different nature than the classical bit. It's to do with superposition. But now there's something further that you can do if you have your qubit. We won't say what it is. Maybe it's the cat or something. You can make it interact with other qubits in a very particular way. Can we say something about that?
Right. So there's two parts to your question. The second is how can we make composite systems of qubits and how we can get them to interact.
And I guess the reason for that is, one bit or even one qubit is not very useful, right? I mean, one bit is on and off. And even a qubit, which is more interesting,
you definitely want...
You don't do much with it.
You
right?
definitely want more than one. Although one qubit, you'd be surprised. It's a very perplexing object in its own right, that you could have something that's in this intermediate state between 0 and 1, or true and false, or whatever. But let me just, before I go into that, you kind of preface that with a remark about we're ignoring for the time being the nature of the bit, how it's instantiated physically. And I think that's actually a very profound and powerful part of this subject and of information theory in general, is that you can abstract out that you don't have to worry about, is the qubit a superconducting object? Is it a spin on a particle? It can be thought of in this more abstract way that then can be multiply realized in any kind of physical system. That's, I think, a profound aspect of the physical world, that we can move to that level of abstraction.
So it means it is a fundamental characteristic of reality.
Depends what you define as fundamental, but yes, I would think that.
Okay.
And it's just the way that any computer can execute any piece of software, maybe not very well, but it can, in theory, do it. And that's actually part of the definition of computer, is that there's a universality to its operation. And so it is with these bits and qubits as well. So the real oomph of the computer, as you point out, comes from when you combine multiple qubits, and the combination occurs in an interesting way that gives the quantum computer its immense capacity and its immense computing power, perhaps. And that is, if you have two qubits, you can say, well, okay, this one can be, say, my left and right hand. This one can be 0 or 1, or some combination thereof, or intermediate state thereof. This one can be 0 and 1. But then there's also the relationship of those two qubits. This actually is quantum entanglement, although usually when you talk about entanglement, you think of things far apart and so forth. We're not going down that particular interpretational road yet. But we're just thinking of forming composite states of qubits. And you actually have extra possibilities formed by the relationships that those qubits can bear. So this one can be 0, 1, this can be 0, 1. It can be 1 is a 1 and the other is 0, or 1 is 0 and the other is 1. So there's kind of, in this case, kind of a 2 by 2 matrix of possibilities, each of which has a number associated with it. So in addition to being maybe 0.32 of the way from 0 to 1 just for a single qubit, you can actually also have numbers associated with these correlations that the qubits can bear to one another. And if you get 3, it goes up exponentially. So it's 2 to the whatever number of qubits you've got. So 2 qubits, 4, 3, 8, 16, 32, and so and so.
And part of the power that comes from that, right, is this entanglement, which I guess would take another evening to really get into, and you should read Spooky Action at a Distance, which talks about it. But this entanglement, it means that if I go and poke at one of those qubits, something may happen to the others. I mean, putting it very, very crudely. And that opens up a whole realm of possibilities, because I can choose to poke at different ones and poke at them in different ways and make the whole system do something. Is that an accurate way of putting it?
It is accurate, absolutely accurate, that there seems to be, I mean, it's a subtle business, of course, whether you should really be thinking of it in terms of that kind of influence, or whether there's some other way of thinking about it. But I think in terms of the quantum computer, as opposed to quantum communications, where this seeming spooky action at a distance comes into play. When you actually think of a quantum computer, I think the way to think about it is the following: that the computer as a whole, so if you have 3, 4, 5, whatever number of qubits, it has information storage capacity collectively above and beyond what each individual qubit can hold. And this is really what gives the quantum computer its immense power, probably. I mean, the power of quantum computers is also a subtle thing, but certainly its immense storage capacity. Is that not only are you storing information on this bit, this bit, this bit, this bit, as you would with a classical machine, but you also are storing it on these correlations among the bits. And actually, the vast bulk, once you go to higher and higher numbers of bits, a vast bulk of the information is in these correlations, not on the individual bits. They kind of just fade away, and you're left with this collective or even holistic system that, and one way to say it differently is that the bits are delocalized. They're held by the whole system. And this is where you get the real power.
So you're smearing the cats out.
The cats are smeared.
So you have
Very smeared.
The Cheshire cat Cheshire cats don't exist, but you have the Cheshire cat smeared out with the black and white cat and so on. And it's this big entangled thing of cat.
Yep.
Which is multiple qubits, but the information is in the overlaps, the interference, the interactions.
Yep.
And that means that for computational purposes, apart from this extraordinary growth in the amount of information, if I do something to that system of qubits, it happens simultaneously throughout.
Yeah, but again, I wouldn't worry too much about the simultaneity aspect. If that comes up in the analysis of what entanglement means and the kinds of
And
things.
I think more in the sense of sort of computational efficiency, like clock cycles in a chip. Is that the way of looking at it? Maybe not.
I would, maybe, but that's not the way I would necessarily approach it.
Okay.
It's I think you're right, but I think I'm coming at it from a slightly different point of view, where I'm not really worried too much about the simultaneity or other kind of relations among these qubits. I'm just coming to the system, and like the system has a certain amount of information in it, and the information, how is it stored? It's not in individual memory locations. It's around the whole thing in a way that you cannot have in a ordinary computer, phone, or whatever device.
Okay, so
far so good.
So far so good. I'm keeping up. I think for me the next step was actually to talk about some of the ways in which you manifest this. You do this in the real world. And I think from my point of view, there are two pieces to that. Perhaps we could talk a little bit about, okay, what is an actual qubit in reality? Is it a cat or is it something else? And what options are there? Mm-hmm. And then also the question of, you've now got this thing that can hold information in very particular ways. How do we step from that to computation with logic gates and a system of logic and so on? But let's start with, okay, I go to the hardware store today and I say, I'd like a quantum computer. It can be a small one, just a few qubits. What are the options? How are these things being made?
You have very good hardware stores up at near
Oh,
your house.
We do, absolutely. It's because of the physics department.
Yeah. So let's break those two things apart. What is a qubit, and how do you operate on one? And if I forget one, someone please remind me of the train of thought, because I do tend to lose it, especially after having some of this beer. So there are, as I kind of alluded to earlier, and as you did, there are different ways to take this abstract idea of a bit or qubit or information in general and put it into a physical system. And I hazard to say that there's two leading techniques, although there are, of course, more, and some of them very interesting. I keep learning about more ways people pack qubits into materials, and it's fascinating. And they have different trade-offs, of course. But roughly speaking, let's just focus on two. One is a superconducting loop, and the other is an ion that's been trapped and held. So I got to actually see one of these trapped ions a few years ago, and it's kind of a trip, because it's an atom, and you can see it with your eye. You, of course, can't see the atom, but you see the light given off by the atom. Light is being injected into it, and it's fluorescing, and you see it individually. It's separated from other atoms. It's kind of, that's what makes it computationally useful, is it can be just on its own. and addressable on its own.
What kind of atom is it? What element?
I think that was calcium.
Calcium. Okay, no, that's good. It's good to hang on to some.
Yeah.
So a calcium atom, you take away some of the electrons, so it has an electrical charge. We call it an ion.
Exactly.
And it can be suspended using lasers and electrical fields and stuff like that.
I don't need me here.
No, and you could see it. Okay,
Yeah.
so what? Okay, so is that atom? Can that be a qubit?
Yes, absolutely. And there's each of these possibilities is like a tree of options that come out of it, but the motion can actually represent a qubit, or the charge, or the oscillations of that system. There's actually different ways to put a qubit into that. Typically, you have a row of them, sometimes a grid, but we'll talk about a little row. It looks like a little Newton's cradle. You can actually, the ions will do that. They will move back and forth because of their electrical interactions. That's how they're coupled together, and you can do computation with that coupling. And because they're separated by a good distance, you can aim your laser at them, and you can set them in motion, or you can excite them to different levels of energy, or however you want to perform your computation.
So that's one. And you said also a superconducting ring. Now, is it this size, or is it teeny tiny?
It's pretty small. It's actually not nano small, but it's actually something you can kind of see with a good magnifying lens. Maybe in the future they can shrink them down further. And here, again, there's a couple branches of different ways you can store the information in, but one might be that one might be in the magnetic flux. So you can think of the supercomputing qubit as a little coil, a little tiny electromagnet, basically. And it can create a magnetic field. It can be like the north is this way and the south is that way, or the other way around. And that might represent the two possibilities. And there's other ways of storing information in the qubit with charge or other things. But let's just focus on, think of it as a teeny, teeny, tiny little electromagnet.
Okay.
And it can interact with other qubits either directly through its magnetism, or there can be an intermediary electrical effect, or an intermediary magnet effect. So there's different ways of coupling them together. So anyway, you've got these ions on the one hand, and these superconducting qubits, little tiny electromagnets essentially on the other.
And just out of interest, I mean, are there other things you could use? Are there other things people are trying to use? I mean, what about photons?
Yep, there is photonic quantum computing as well. There's an information storage issue with photons because they don't like to stand still. But there's actually a lot of interesting work on that. These two methods of ions and superconducting qubits seem to be at present the most scalable of the techniques. But though I just learned February, I guess it was, about another kind of cool and up and coming possibility, which is actually just using our existing integrated circuit technology with transistors, your Intel Inside kind of thing, and change the voltage on the transistors so that they hold a single electron in them. And then the single electron can serve as a qubit as well. And the nice thing about this is there's an established technology for fabricating these kinds of circuits, and a technology to use them.
That's quite something.
It's actually, it could be a leapfrogging kind of technology, and it's being, I think the leading group is in Netherlands, is in Delft.
And just to round this off, I mean, right now, these machines, so we have superconducting elements, so they've got to be kept cold. So there's all sorts of peripheral equipment. I mean, it's not something that's going to be in my pocket anytime soon, necessarily, at least not right now. And presumably these traps that hold the ions, that requires essentially a laboratory of infrastructure.
Yeah, I mean, these are as much physics as actually more physics than engineering projects, at least currently. They're massive. So IBM has what's it up to, 20 qubit processor that's actually online. You can actually register for it and go and use it.
I even thought about whether we should do this and have so you can go to a website, you can log in, and you can play around with IBM's quantum computer and actually try to run little problems.
Anytime you try to do internet thing during a presentation is going to fail.
Yeah,
So
yeah. And also, it would require me having to learn how to do that. And
it's pretty easy to set up, but yeah, you do
but
have
if
to.
you're interested.
It's cool. And so I've actually seen the physical, it's up in Yorktown Heights. I've seen the physical device, and they've got it kind of off in a room with kind of spooky blue lighting around it, and it makes it kind of cool. But it's a fairly large apparatus. It's the actual system itself is quite small, but it has to be, as you say, kept, in this case, quite cold. It's superconducting, so it has to be kept down at, I don't know, in this case, 4 Kelvin. Probably a bit, maybe, I don't know what superconductor they're using, but quite cold.
So, okay, so now, all right, so I'm trying to be systematic for my own sake. So now we've got we've got a rough idea of qubits. The picture of the cat helps me a lot. We've got an idea of what you get out of having a bunch of qubits entangled, that great increase in information content. We've got an idea of how you actually manifest this, at least today. So now I've got my thing up at IBM in the big refrigerator. I've got my ions, and I want to do something with it. So in classical computing, right, we have this whole scheme of Boolean logic. Okay, I can have gates. So I can have things like an AND gate, which if I have 2 inputs and at 1 output, I only get a 1 coming out of the output if I have 2 1s coming in. So it's an AND gate. That and that have to be 1 in order to get a 1 out. Or I can have an OR gate, right, where it's either of those inputs can have a positive, have a 1 coming in, and I'll get a 1 coming out. I can have not. So there's this whole architecture of logic, right? Classical bit-based logic. How does this work for qubits and quantum computing? What's the deal?
Yeah, no, it's a great question. I should say that the intuition is essentially the same. In fact, really, the quantum computers were designed with that earlier classical Boolean logic in mind. So there's no coincidence that the same principles carry over. And later, I hope we can come back to some of the entirely new computing paradigms that don't translate or aren't direct translations of this classical intuition. But yes, there's the idea is that you have these discrete units of information, qubits. You've got a clock that's regulating the system. So at each, there's a series of stages that one goes through, step 1, step 2, et cetera. And at each of those stages, an operation is performed. And there actually are quantum analogs of all the gates that you described. The one that's commonly used is actually a NOT operation. There's a subtlety here in that the operations need to be reversible. So the operations you talked about actually were not directly reversible. So in this case, in quantum computing, you use gates that have 2 inputs and 2 outputs, so you could always just back out. You could run them backwards.
So let's just so like in classical computing, the NOT gate, right? Or I guess let's see. That's probably not the right example. An OR gate. If either of 2 inputs is 1, I will get a 1 out the other end. But if all I have is that output, I can't go back and figure out which one was 1 in the first place.
And actually, I should say
a way to think about time reversibility in this sense?
In this context. And this is actually taking us down a slightly different corridor but just to complete the thought so we can go on. In classical computing, there actually is a theory of reversible gates that one might apply. And maybe in the future we will, because it actually potentially can reduce the energy consumption of these machines, but we'll put that aside. So a lot of the quantum computing architectures actually are based on that kind of alternative pathway of classical computing. And so the one that often is talked about, because it's extremely powerful and actually is a part of a universal set of gates, is what's called a controlled NOT gate. And it's like a NOT. If whatever comes in is inverted. So if you have a 1 coming in, 0 comes out. If you have 0, 1, or some intermediate state that's also inverted coming out the other side. So it works on these superpositions. And it's the controlled aspect of it is that there's an additional input. So there's 2 inputs, 2 outputs with this, where the state of the control bit determines whether the gate is operating or not. So if it's 0, no inversion occurs. If it's 1, inversion occurs. And again, there's an intermediate set of possibilities that you could have. So that's a 2-qubit gate. It allows pairs of qubits to be combined and interact and perform computation. You would obviously need that because you're trying to composite all these qubits, and perform your computation. Then there's additionally a set of 1-qubit gates, which just allow you to act on a single qubit and manipulate that qubit in various interesting ways. So 1 actually will put the qubit into a superposition. See, it would be kind of the equivalent of, is the cat alive or dead in the Schrodinger thought experiment. You could take a cat, make it in this kind of purgatory state, and then actually remove it from purgatory later if you so desire, and if you're nice. So that allows you to create superpositions, and then there's other kinds of gates that allow you to kind of muck around with the superpositions and flip them around and kind of this. Because it's an analog, as I said at the outset, it's an analog device, you kind of need a couple of these extra additional gates to really make full use of the analog power that you can exploit the whole state space that the qubits provide you.
Right. And my understanding is some of these gates are things like applying an electric field or magnetic field in a particular way, or targeting, as you say, 1 qubit and so on. So there's a whole variety of ways that is manifest.
So it might be applying a pulse, a microwave pulse, either of microwaves or of a electrical signal at microwave frequency that would then cause the qubit to begin moving essentially, or begin evolving, and then you stop it later, and when you get it to its right place, you kind of apply pulse for a certain length of time, the qubit rotates or what have you.
Yeah, so it feels very much like you have this thing, these cats in a box, and to my mind, compared to a classical computer, although maybe there's a certain similarity, it's almost like I have this thing, and I'm like poking it, and I'm doing things. I'm waving a wand. I'm blowing pixie dust over. I'm doing all these different things, each of which corresponds to a very specific type of action and gate and logic. And then something is going on inside there that, if I do this right, is gonna do computation for me. I mean, that's putting it very crudely, but there's an element of, I hate to say black magic here, right? It feels that way a little bit.
Interesting.
I mean, I don't think it is, but it feels almost artistic.
Yeah, I think it's interesting you say that. I think it's just one of these cases where we could just sit maybe we'll do it later, the back and go through some of these examples, and it's pretty spelled out. Once you have gates that can do certain things, you assemble them in certain ways, and there's the art or the kind of creativity coming into it, and then you get an output. It's like forming any kind of algorithm. If you're doing a search algorithm in Computer Science 101, it's similar to that. And now there's Quantum Computer Science 101, where you ask, what can you do with these sets of gates, and you can run and I'm segueing for you.
Yes, and so I feel like we've kind of done the 101 attempted 101 course in the absolute rudiments of quantum computing. We should get to the meat of it. Let's jump to part of why we're sitting here, which is the application. So my understanding is that there are particular computational problems that this kind of system seems to be well suited to. And one of those is to do with what we presently tend to call AI. It's really deep learning systems, neural net systems, and how those work, which, I mean, the majority of what we call AI systems kind of based around this underlying architecture. So let's just jump right into that.
Before we jump in, let me just make one preface, kind of riffing off part of what you're saying. So the quantum computers have this incredible power to them. But remember, the power is at this kind of analog level, whereas we need to extract information at the digital level. So something can get lost in translation between those two. So as powerful as the quantum computer may seem a priori, it actually is remarkably difficult to really harness its power. And there's probably, I don't know how many fingers I would need, but there aren't that many algorithms that show a definite advantage over their classical counterparts. The one that often gets talked about before we get into the machine learning aspects is factoring numbers.
Right.
Another is basically brute force search. There's a type of search that a quantum computer can do that it's somewhat faster than the equivalent classical search. There is matrix inversion. There's some other things that are kind of harder to really boil down into a pithy phrase, but there aren't that many algorithms. So what makes the machine learning aspects so interesting is that, wow, maybe we can actually use one of our limited tools in our tiny little toolbox and tackle one of the great computational questions of our time.
And that's because there's this coincidence, if you will, between the needs of current deep learning systems, or many current deep learning systems, and you mentioned it already, matrix inversion, matrix manipulation. So, I don't know, can we say that in like a few sentences, how those two things...
Depends how many semicolons you give me.
I'm sorry?
Depends how many semicolons I can use to pack my sentences together.
Well, we'll see.
So, I mean, there's a couple ways to think about this, but first of all, the bottom line, get it out there, is that in interesting ways, quantum computers seem quite well suited to machine learning. It's almost, they're almost made for each other in a way, which is kind of interesting in its own. So, and there's a couple ways you can arrive at that kind of that harmony between the two, and one is, as you say, matrices. So quantum physics is largely an exercise in matrix multiplication, diagonalization, everything you might want to do with matrices. And that's also what neural networks need. So when a neural network runs in a data center for Facebook, Google, Alibaba, all the others, it's running in some data center, usually on graphics processing units, because when doing computer graphics, you also need to manipulate large matrices to do rotations and such like. So the matrix element comes up in neural networks a lot, and quantum computing seems extremely well suited just by its very matrixy nature to that. But another way to think of it is going back to what I said earlier about the kind of wholes greater than the sum of its parts aspect of the putting a lot of qubits together. The brain is like that too, or an artificial neural network is like that too. You put a lot of dead simple elements together, and these quantum computing, these neural networks can be built out of just switches, just things that are on or off. And there's more sophisticated versions, but that's the simplest. And you get this incredible richness of behavior where you can play Go and chess and everything out of just oodles, billions of these elements. So both neural networks and quantum systems seem to have this wholes greater than the sum of its parts quality to them that also makes them well suited to one another.
Right. Which is pretty extraordinary.
It's pretty great. I mean, it's pretty cool. I think this is really very striking that it's the case. And there's subtleties, of course, with it. One might have wondered, one need not be hypothetical. People did wonder whether neural networks would ever work. And people did wonder whether quantum computers, and do wonder whether quantum computers really could work.
And it's interesting.
And yet they do. So it's kind of this cool, wow, they work.
And part of the near history of deep learning systems, neural networks, is that you had to make them complicated enough, and then you kind of get to the next level. So, the typical architecture, putting it very crudely, are these layers of virtual neurons. The neurons in a artificial neural network are just, like you say, essentially an on-off switch, but they're triggered by a certain number of inputs reaching some threshold, which sort of mimics something about how biological brains work, but in a very, very simplistic, abstract way. But you have layers of these things, and each of these artificial neurons is connected to all the ones in the previous layer, and so on. And then you showed a picture of a cat. This is a live cat this time, we'll say. And, basically the data from that image gets turned into little numbers that are associated with all of those connections. And the training of the neural network is often an iterative process. You show it this, and all of these numbers get added up across these layers of neurons, and some number gets spat out, which says cat or not cat. And if it's wrong, you correct it. You tell, no, this is a cat. And so somehow, without going into the details of how this works, the system kind of shuffles itself. It gets, shaken around, and eventually it finds the way to extract the information that's necessary to say, there's a cat. And we don't necessarily know what that information is all the time. But the immediate history of it is that people had these layers of neural nets, or layers of neurons in the artificial neural network. And maybe they had 4 or 5 layers, and you could do a certain number of things with that. It wasn't until people tried putting 20, 30 layers together in very specific ways that suddenly you could perform some of these essentially cognitive tasks. So it's pretty remarkable that it's not just the architecture, it's the level of complexity required is something that well matches the potential of quantum computing.
Yeah, and conversely, it's a very computationally demanding exercise that demands a proportionately powerful computer. Welcome quantum computer. So I should say that it's interesting, just personal history here. The very first science article I ever wrote, very first science kind of journalism I ever did, was actually an article on neural networks back in 1986, I think it was. I was an undergraduate. And they were actually pretty good back then. And then they went into this AI winter that occurred before they achieved their recent successes. So it's one of these technologies and computational paradigms that have kind of gone in and out of favor, partly on their own merits, partly for lack of technology, partly for sociological reasons. And now we're at a peak again, or at least we're on an upward slope again.
Right.
I hesitate to say peak.
So, there's a couple more things I want to talk to you about, and then we'll have time for some questions. So something we probably won't go into in any detail right now, maybe I'll just mention it just so people are aware. You're actually getting information into a current quantum computer, getting answers out is difficult. It's practically difficult. There's noise. There's difficulty in keeping the qubits entangled, keeping coherent so that the system actually does what you hope it will do. So there are all these other technical challenges that are there. But I wanted to get to this arc.
Okay, let's do it.
Which is, okay, this all sounds really good. This kind of sounds like, maybe not right away, but at some point, we're going to have this exponential growth in what we can do with deep learning systems, what we call AI today. So does this mean that we're going to have, with quantum computing, the general intelligence, the general artificial intelligence, the conscious machine, the thing that somehow replicates us at some level? Is there a connection here, or is that just wishful thinking at this point?
Wow. Okay, where should I begin?
Have another drink.
Yes, good idea. Always a good idea.
I will too.
So, a couple of different ways to approach this. Quantum computers aren't magic. They're not infinitely powerful devices. They cannot solve NP-complete problems. That's something that kind of got out there, and it is just not true. They can solve a somewhat wider category of problems efficiently than classical devices can. In interesting ways, the factorizing numbers, for example, doing some search, maybe doing these matrix calculations. But they still have limits, and it's not clear whether they add that much to our current AI systems. Now, not clear doesn't mean they don't. That just means it's genuinely not clear, and it's a subtle business. And the reason it is something you mentioned, the difficulty of getting information in and out of them. So as powerful as they may be, if you can't get the information in and out efficiently, the power goes unharnessed. So the worry is that any computational advantage they may have inherently is offset by this input-output problem.
Because there's this, I mean, I just want to mention it because it's something that gets thrown around. I've heard people say it. I mean, I think we've all written something to this effect. You know, there is this interesting fact that I've forgotten how many qubits it is. Is it like if you have 200 or 300 qubits in principle, you could put the information for every single piece of matter in the entire observable universe in your quantum computer. So you could simulate everything down to every fundamental particle in the entire universe.
You could store it, whether you could simulate it.
Okay, you could store it. But you then have to ask, well, how long is it going to take me to put... So I think in the observable universe, there's 10 to the power of 80 particles of normal matter. Okay, so how long is it going to take me to enter all of that information into my quantum I put that out as a one example on the extreme end of the challenge of, you know, you have big ambitions, but there's a practical side to this.
Right. So, and then the next kind of, you're exactly right. So certainly for, when you talk about being able to store the entire corpus of human knowledge or the entire Facebook photo corpus or whatever, you have to be able to get it in the computer. So, okay, so then there's the question of, it might indeed have a computational speed up for certain kinds of problems, and it will. I think it's pretty clear already that it will. There will be some problems for which, despite these input-output difficulties, it works. But then the question is whether you've narrowed your problem definition so much that actually a classical computer could do well at it. So if you've given the problem enough structure, then you have to be kind of fair to the classical computer and say, well, if the problem has this structure, could you solve it fast too? This is why there's just so few known algorithms that quantum computers do much more efficiently than in a classical machine. Factoring really being the top one, and maybe a couple of these other ones. But still, I think all these caveats aside, there will be a role for quantum computer, just as there's a role for GPUs in our machines today. You don't use the GPU to run your word processor or what have you, but you do use it for some kinds of mathematical problems and certainly for playing games or whatever. Likewise, the quantum computer will be a coprocessor for regular computers, for classical.
So I will go to the hardware store or the Best Buy or Amazon at some point, maybe, and say, okay, I want a quantum card, or I want the quantum add-on to my MacBook, and exactly. I can go and get that, and I need a really good USB cord because there's going to be a lot of back and forth. But that may be
USB Q or up to by that
USB
point,
Q. There we go. Quick, let's get a copyright on that. So that's very interesting. So in a sense, there are going to be hybrid computers always.
Even today, the glimmerings of applications really are in this kind of hybrid category. And really, all computers are hybrids in some way or other. So it's not that unusual to say this, but certainly when you get into some of the machine learning applications of quantum computing, they're definitely going to be hybrids. So, the quantum computers, given the kind of hard, computationally inherently intractable part of the problem, you go off and do that. And one that comes up is if you have a collection of neurons given certain interrelations among them, how will the system settle out? What kind of equilibrium will they reach? So if this neuron, well, actually it could be an electron. If this neuron is connected to these other neurons, and it starts in a certain state, how will that state propagate, and the whole thing kind of settles into a final condition? That's very hard to do. So that's the kind of task you would give to your quantum computer. And then once it settles, the classical part of the hybrid will then say, well, it seems to be that to make it settle to a different state that has the properties we want, maybe lower energy, for example, because you're trying to reach the lowest energy state often in these problems, we need to tweak the parameters So the tweaking will occur kind of in a classical device just with ordinary arithmetic, and then the couplings and states of the neurons implemented as qubits will be adjusted, and the thing will run and again it'll go in a loop until you settle down into what you want.
It needs to be nursed a little bit.
Yeah.
It needs supervision to make this.
Yeah,
make
and again,
this
I don't
work.
think that's different from the way our brains operate. We have many brain modules. Obviously, we need them, and any ordinary computer has multiple, even on the same chip, can have multiple functions, and then certainly we have coprocessors. Well, on a quantum computer will be another one of them.
So since you mentioned the brain, there's so many avenues we could keep talking about here, pursuing, and the nature of even modern quantum systems. Like there's the D-wave system, which I know has almost a completely different kind of use of quantum effects to perform computation, but we really don't have time to follow. Maybe questions can come up, but just to end our little bit of discussion before we have some questions. So you mentioned brains. And I wanted to get to this, and I know that I think we both share skepticism, but I wanted to say it as completion. Over the years, and it's related to quantum computing, but it's also related to quantum physics and the nature of biological brains. There have been some infamous statements or even whole books written by respectable scientists talking about whether biological brains, human brains in particular, actually are exploiting something like these quantum effects. They're exploiting things at a quantum level in order to become greater than the sum of the parts. The reason we can do certain types of mathematical problems that would keep a computer in a perpetual loop forever has been attributed by some people to the idea that there's something mysterious and quantum happening in our brains. Now, I just wanted to say a little bit about that and ask your opinion on that, because I think like me, you're skeptical. Part of it is that our brains are warm and wet, and it's very difficult for these things like quantum superposition and entanglement to even happen in those environments. We talked about how the extent to which you go to make a functioning quantum computer, you've got to refrigerate things, you've got to tweak it, you've got to keep it encased and do all sorts of things to nurture it. Let's just go there for this last couple of minutes. Anything to this? Is there something deeply mysterious about our brains to do with quantum physics, do you think? Apart from chemistry, which is quantum.
I was just at a conference last week, the one that was organized by Stu Hameroff and Roger Penrose, who are the leading advocates of this kind of view that you're describing. And this is the second year I've gone to their conference. It's actually a fascinating conference. So I think there's different levels on which you can think of this. Kind of progressively more radical in a way. So are there quantum effects in biology, in biological systems? And I think, it's still a somewhat contentious subject, but I think seems to be yes. There are some. The leading candidates, again, it's still being worked up, but the leading candidates for that are bird navigation, that essentially a superposition is created in a bird's brain that is affected by the Earth's magnetic field, and how the interference pattern that results can tell the bird where magnetic north is. It can actually literally see it in its eye. That's one possibility. Photosynthesis and the energy transfers that can occur there. That's something, of course, you're an expert on. So that's the first level. Are there quantum effects in biology? It seems there could be. Then there's the question of, are there quantum effects in us? And there, actually, I went to a very interesting talk by Christoph Simon. He's at Calgary. And he made an interesting argument that it's quite plausible that there are some quantum effects in our brains, even at the kind of level that Penrose and Hameroff have been talking about, which are within neurons. They're actually within the cytoskeleton of neurons in these particular kinds of proteins. The axon between neurons actually has the properties of an optical fiber. It literally, if you put a photon into one, it will travel down the optical fiber just as surely as it would into your stereo or into your back of your computer, whatever you use your fibers for. And there are candidates for photon detectors and single photon detectors and photon emission within the brain. More speculative, but completely empirical. One could test these ideas, and they are actively being tested. Then there is the idea that maybe consciousness, our subjective experience and the qualities that it has, could be connected somehow with quantum effects. And this is where I begin to get more skeptical. I don't think it's out of the question, actually. I'm less skeptical, perhaps, after going to these conferences than I used to be. And why? Well, there's a couple kind of a priori reasons that makes it conceivable. One is that actually the earlier concerns about the unfavorable environment in the brain, the warm, wet conditions, are looming somewhat less large because naturally we do have some computational devices that also work at room temperature. There's ways to protect the quantum states, encoding them in certain resistant forms. There's parts of the biological system. Often those calculations are done in water solution, but there's also oils and lipids that the quantum processes might conceivably take place in. So there's that. Then there's just a kind of broad point that if quantum computers are possible, and we think that they are, then nature in its billions of years of evolution might well have stumbled across it. It's not a heavy lift on that intellectually. Now, I think for me, the possibility kind of then becomes problematic when asked, come up with a specific theory, a step-by-step set of mechanisms that lead to phenomenology. That, I think, that's where the theory comes down. But again, it's okay. Let's sit back. If they come up with a theory, it can be tested, and it arguably is being tested. So, and then there's an even more speculative level, which is that our consciousness affects the quantum. It doesn't go from quantum to us; it goes the other way around. And this actually goes back to Bohr and Heisenberg and Wigner and some of the founders of quantum mechanics, and that, of course, would be pretty radical. And again, it is a testable concept. It's not outside the bounds of empirical science. So bring it on. Let's test it. So I think that's a kind of spectrum of possibility that one has to parse on this.
That's great. So I think I want to thank you, but we're going to do questions. So thank you, George.
Thank you very much.
That was quite a tour de force. I hope there's some questions. Let's have some questions. There's one right here. We'll get a mic to you.
All right. Thanks so much. It was a very entertaining discussion, so very useful. Going back to the last topic about consciousness and the brain, I'm very skeptical about any Penrose hypothesis about quantum effects in the brain, and I wanted to say that given the power of any quantum computation, where we saw that with 200 qubits we will be able to obtain a very large amount of computation, I wonder why then, if the human brain is able to tap into quantum computer, evolution had to go from C. elegans, which has only about 200 neurons, to something as about 65 billion. If quantum computing was emerging through evolutionary path, I will expect some very steep rise of the level of consciousness in animals, and I think there's more like a continuum. So I'd like to ask you what you think about that.
Yeah, I think that was kind of implicit in my. I agree with your skepticism. Did everyone hear the question? Should we repeat the question?
I think people heard it.
Okay. Yeah. So I'm skeptical in the same way that you are. And one thing that we've talked about, which I actually didn't mention, but I'll add now, is that the brain already has an enormous connectivity in it. Just huge, more than even our artificial neural networks do. So there doesn't seem to be any necessity in explaining human cognition and perception. We don't need to resort to these quantum effects. This is why I think maybe some of the earlier stages in my continuum are somewhat more plausible. There may be an effect here and there in the way that bird brains don't rely exclusively on quantum effects, but there may be this one aspect of their perception that involves a quantum effect, so there may be in the human brain. I'm not saying that there is or there isn't, but it's not an implausible thing to say. Of course, Penrose was coming at this when he came up with these ideas, what's it been, 30 years, And actually, I was a graduate student when Emperor's New Mind came out, and Penrose came to where I was studying and gave a series of lectures. And it was, even to have an eminent scientist broach these topics was so empowering, especially to a young graduate student. Just to, even if it's wrong, it's such a fruitful and interesting concept, and it helps us to broaden our thinking on this. And maybe, as always in science, right answers come out of wrong reasoning. So the development of electromagnetism in the early part of the 19th century came about from some of the nature philosophy in the German Romanticism, which thought in terms of unity of nature. And they actively went out determined to find a connection between electricity and magnetism. And they found one. Not for the reasons they thought, perhaps, but they found one. And so what I think it will be with the Penrose Hameroff program, that it's provoking such an amount of analysis and experimentation on the brain and new ways of thinking about these problems that it will yield something.
It probably also empowers people like Deepak Chopra to spread a lot of false knowledge.
That always is the case. I will say with Deepak, I mean, he's come to some of these YHouse. He's such a nice person. He's very open to this. So if he comes and he talks to you, by all means, he'll be interested in what you have to say. He has a particular agenda that I don't buy into, but he's really curious about getting the science right. So I wouldn't assimilate him into people who are unconcerned with that. I think he's trying to make sense of the world in a different way than I am, but he's legitimately trying.
Thank you. I'm kind of curious, if you read the mainstream media with regards to quantum computing the last few years, is basically the sky's falling, the end of cryptography is going to happen, and your data is no longer going to be able to be protected. So can you talk about the effects of quantum computing on cryptography? What forms of cryptography that it won't actually have any impact upon, because that's never covered in the media. And then also, there is post-quantum cryptography that is going on in research in that. And so can you talk a little bit about that?
I mean, it's a fascinating subject, the implications of quantum information processing for cryptography, and it's a give and take kind of situation. So on the one hand, the ability to factorize numbers would undermine a lot of our current cryptographic schemes. There might be kind of just by going to larger keys, a way to get around that, but certainly some kinds of codes can be broken by a quantum computer, but at the same time, quantum computing adds to our toolbox in cryptography and lets us send information in a way that's potentially any interception that occurs with the information would reveal itself. And then there's this question of post-quantum cryptography that you bring up, which is there are types of codes that, by their very nature, and I'm not familiar with this, I'm just giving you the extent of my knowledge, that are inherently resistant, even the kind of factorizing strategies that undermine public key cryptography. There actually was a session on this at, I think, the World Science Festival last year. I don't know if they'll be at this year's festival. So it is getting out. I don't know, I can't speak for all the media, but I mean, there has been some kind of attempt to get this information out. So maybe I should write about it. Who knows?
Yes. Okay. In the middle there.
So this question is the fruit of my own ignorance about anything quantum, but the first gentleman's question about there being 200 qubits, not like, you can represent the entirety of the universe, and then mapping that to 65 billion neurons inside of an individual's head. That sort of seems to rest upon the assumption that an individual qubit is the, you need this lowest level. You need to have an atom to get something that exists in a quantum state. And I don't personally know, is it possible to have something that's far more complex, like, for example, entire systems or maps of neurons or entire parts of the brain devoted to a certain purpose that exist in a quantum state? Or do you have to be at an atomic level to have a quantum state you can exist for computational purposes?
I mean, the easy answer is that no, you don't have to be an atomic level. One I think, misconception about quantum mechanics, and then I'll try to get more specific, but just make a general point about the theory. It's not just a theory of atoms, that's how it was invented. It was invented to understand atomic transitions and behavior of light at the photon level. But we are quantum. Just, you literally could put a cat, if you had the equipment, into a superposition of life and death. I mean, it's these, though their thought experiments are quite real, and that actually was Schrodinger's point in that experiment, is that everything is quantum in the world, including us. So yes, one might imagine ways that fairly large-ish systems, not just atomic systems, could be quantum. I think the record holder on the size is actually like a little springboard. It's a little micromechanical resonator, which you can just about see with your eye. It can be put in a superposition of vibrating and not vibrating. So you would always perceive it as one or the other, but nonetheless you could see that system. Now, with regard to the brain, the proposals that people have been talking about are indeed at a molecular level. If there are quantum effects in the brain, they would occur at that level within the neuron or within the glia, there's some people are proposing. So they're down there. They're down at the protein or even benzene ring level of this. And then one of the challenges of that kind of account is that it then has to be brought back up to our level in a way that preserves the quantum information. That's part of the theory that is less well developed. I don't know if I'm really answering your question. Your question is quite broad, as was the first person's question. We can talk more afterwards if you'd like.
Do we have time for more questions?
2 more.
2 more. Excellent. Gentleman here, right at the front.
Thank you. It was a very nice conversation. But I have actually a very basic question. It's like I'm just trying to wonder, like, what is the minimum? What is the most indivisible value right now? Is it like the Planck's constant something? I just want to clarify.
So what's the kind of smallest unit
Yeah,
of?
the smallest indivisible unit, like which would be true in any universe, in quantum universe, maybe in this here or maybe in any other galaxy or whatever. That's the constant thing.
Yeah, so the smallest unit, or the quantum,
Yeah.
that's where it comes from.
Yeah.
Actually, it varies. It's completely context dependent. So a red light, the smallest quantum of energy the quantum of energy is smaller than it is for, say, blue light. So it depending on the size of your system, the quantum can vary.
Okay, so just let me rephrase. So what I was trying to basically understand is, like, is there something which will be same, suppose, in this universe, or suppose there's in another universe? Like I'm saying, like trying to identify what is the most fundamental unit which will be the same throughout, which will not change basically. Is there something like that, or?
If we're going into other universes, then I think.
No, I'm just saying, like, that's a
yeah,
thought.
no,
like,
no. I think the answer is that we don't know, and I think what George is getting at is, there are different ways to think about the quantum nature of things and particles. We talk about particles, right? But really, at a slightly deeper level, in quantum field theory, a photon of light is an oscillation of a field, which is slightly more abstract mathematical thing, and that is analog. Actually, it's just that it has some minimum value in a particular system that we associate with a quanta of energy. Mm-hmm. But it's underneath that, it's analog, right?
Yeah,
which means there's no, in principle, it goes all the way down.
I mean, it depends a lot on the system and the specifics of the theory that you're talking about. But often, the appearance of discreteness in a quantum system come from some kind of boundary condition that you put on the problem, or some kind of self-consistency condition. It's just like a string on a guitar can oscillate at the various harmonics of that, or depending on how you fret it, of course. But there's a discrete spectrum of possible vibrations of that string or of any instrument based on the length of the string and the tension within it. So it is with the quantum. Depending on how you kind of bracket the system, things can oscillate in different ways, and the unit of oscillation will be different. Underlying everything does seem to be this continuous structure, and it's actually kind of interesting that we have these 2 levels, this analog and this digital level of the quantum realm. I don't know if it answers your question. Come to me afterwards and we can talk more.
Sure, I'll talk after.
So we have time for one more question, and I think got it over there.
Hi. So, what are the top engineering challenges that are there today to make quantum computing, like a lot of these theories, be proven or not, and to make it a reality in the practical world?
So many. There's just so many. I mean, it's
So-
kind of interesting. So, one is just the difficulty fabricating a lot of these devices, certainly at the scale that's required. So when, for instance, some of the superconducting qubits, someone has to fabricate a wafer with it, and there's going to be some kind of manufacturing defects in that. And sometimes, and this is true of the D-Wave computer and some of the other devices, they've created, say, 49, 7x7 grid of qubits. Maybe some of them just are not operative, and that creates a noise there. Then there's the control signals that have to be applied. And there you kind of have a trade-off, as you do in every engineering application. You want to be able to affect the quantum system from the outside, but in affecting it and allowing an influence to get into the system, you're also disturbing it. And that's a source of error as well. Then there's actually even more subtle trade-offs having to do with sometimes when you operate just on individual qubits, doing these kinds of superposition transformations or rotations, the better you can do that, the worse you are at doing 2-qubit operations that couple qubits. So you've got to make a balance between the ability to operate on a single qubit versus the ability to pair them together. And they're kept at low temperatures for a reason. You want to reduce thermal noise in the system, and the coupling that occurs between the system and its surroundings you need to minimize. I mean, I talked to John Martinez, who's one of the leaders. He's at the Google research group. It's actually at University of California, Santa Barbara. And I asked him, I don't know quite how this came up, but there's a session where Google was speaking, Facebook was speaking, all the big companies were there, Microsoft. I said, do you feel this kind of competition, with these other companies? He said, right now we're competing against nature. We don't even really register the competition between Microsoft, Google, IonQ, and the other companies. It's just so freaking hard to get down these error sources.
You had mentioned the problem about putting data in and out of the system.
Mm-hmm.
Is that what you're referring with the process?
Yeah, so in order to... Sorry?
So isn't there more fundamental thing, the way we think about data, that would have to be changed to work with quantum computers?
The data will still come out in the way we've always thought about data. It will come out as a string of bits. The aspect of our thinking that needs to change is that prior to the extraction of the data, the quantum system will generically be in some kind of superposition state. So in extracting the data, you are forcing the system to collapse down. So it exits its superposition and enters just one of the multiple possibilities that had been open to it. And you don't want to do that too soon, because you'll just get random hash out of the machine. You want to wait till the machine is most likely to have the right answer. It's all probabilistic here. And then once that probability is maximized, then you go in. And that's the aspect of our information theory that's going to have, it is changing to take into account the nature of the quantum computer. I don't know, does that answer your question, or?
Yes, so it's just a follow-up.
Yes.
So is that more related to engineering materials so that that state gets there sooner? Is that what it's about?
So there's both a physics and an engineering component to this. The engineering component is you have to make sure that the bits are stable and controllable and can be operated on long enough to perform your computation and don't lose their information. And it's like with any computer. The physics side of things is that there's a more fundamental thing going on here. Even if you had an engineering, a system that's perfect at the engineering level, you'd still have inherent physics limitations on the ability to extract knowledge from that computer. And that's because the computer might be in a superposition of 0 and 1. And if it were in an equal superposition of the two, then measuring it is going to give you 0 or 1 randomly. And that is not a useful piece of information. You want to steer the probabilities so that it's mostly, for instance, mostly 0. It's like 99% chance of being 0, then you actually get some useful information out of the machine. So it's a combination of physics and engineering trade-offs. If I'm not getting at your question, come and talk to me afterwards, please.
I think for time purposes, we're going to have to stop there.
Great
so
questions.
Let me just thank George very, very much for a remarkable discussion. And just end by saying, if you're interested in more stuff like this, take a look at YHouse, yhousenyc.org. We're Y with the letter Y. You can go to our website, see all the kinds of things we're doing. We're also always interested in people who want to be involved with us and volunteer to help us. We're a startup, non-profit institute. Many of us have day jobs in other institutions. I'm at Columbia University. My colleagues are at the Institute for Advanced Study in Princeton and so on. So we're always looking for people who are interested. Thank you so much. There will be more events like this at Caveat. We also have an event called Consciousness Club, which is more informal at our space in New York, down on 28th Street, and you can again find information online. Thank you all so much. Thank you once more, George.